My name is Pawan. I am here to present an Stld seminar on flip-flops and their conversion fundamental and technique. What is a flip-flop? At its core, a flip-flop is a basic digital circuit, meaning it has two stable states which allows it to store a single bit of data. It is fundamental building block of a digital memory. First one, memory element acts as fundamental memory element in sequential logical circuits, remaining its state until expelling change. Clocked orientation changes its state only on the triggering inputs, often synchronized by the clock pulse to ensure orderly data processing. Digital fundamentals forms the basic for the more complex digital complement components like registers, counters, and the memory units in modern computing system. Four main types of flip-flops. Each type offers unique characteristics suitable for different application in digital design. SR flip-flop, the simplest form with set S and reset R inputs. However, it can either an invalid state when both S and R highly simultaneously. JK flip-flop, an important over the SR type. The JK flip-flop eliminates the invalid state. It can toggle its output when both J and K inputs are high. D flip-flop, also known as data or delay flip-flop. It has a single data input D. It is ideal for the storing a single bit of information and avoiding invalid states. T flip-flop. The two-glet flip-flop changes its state on each clock pulse only if its T input is high. It's exactly for the frequency division and counters. Why convert flip-flops? Conversion between flip-flops types is a virtual skill in digital electronics, offering significant advantages in designing and optimization. First one, circuit customization. Different flip-flops types are better suited for specific circuit needed, such as timing, control logic, or power efficiency. Enhanced flexibility. It provides design flexibility, enabling modification to circuit behavior without requiring drastic hardware changes. Circuital for rapid prototyping. Resources optimization. Conversion allows engineers to reduce existing flip-flops components in a new design, reducing metal cost and complexity. Turbulence shooting and debugging. Understanding conventions helps in an dialogical and fixing issues in sequential circuits, making the debugging process more efficient. The conversion process. Converting one flip-flop type to another involves a systematic approach combining characteristic equations and logic design. First one, define requirement. Start by identifying the characteristic equation and truth table and of the decided flip-flop. Utilize excitation table. Consult the excitation table of the available source flip-flop to determine the inputs required to achieve each state transition. Derive Boolean expression. Develop Boolean expression for the inputs of the source flip-flop based on the present state, next state, and inputs of the target flip-flop. Simplify logic. Simplify this Boolean expression using techniques like K-map or Boolean algebra to minimize the logic gates needed. Implement the circuit. Finally, implement the conversion circuit by adding the necessary logic gates to the input of the original flip-flop to achieve the dis, discrete behavior. Example for conversion process. SR flip-flop to D flip-flop conversion. Transformation and SR flip-flop into D flip-flop demonstrates how simple logic can alter functionality. D flip-flop behavior. The D flip-flop's next state Q of T plus 1 direct flows its single data input D. It is designed to store the value present at its D input when clock. Estimate the invalid state issue found in SR flip-flop. Conversion logic. To achieve D flip-flop behavior and the SR input must be controlled by D. The characteristic table of the SR flip-flop is used in conjugation with the described D flip-flop behavior. The simplified Boolean expression for the SR inputs becomes S equal to D and R equal to D dash. This means an invert is placed between the D input and the R input of the SR flip-flop. Example SR flip-flop to JK flip-flop conversion. Converting an SR flip-flop to a JK flip-flop eliminates its problematic invalid state, exchanging its utility. JK flip-flop advantages. The JK flip-flop resolves the invalid state S equal to 1, R equal to 1 issue of the SR flip-flop. It offers a two-glet state J equals to 1, K equals to 1, where the output flip-flop with each clock pulse. Conversion strategies. The inputs J and K of the target JK flip-flop are used to derive the S and R inputs of the available SR flip-flop. The conversion logic ensures that the SR flip-flop never enters into the invalid state. The resulting logic for the S and R depends on J, K are the current states Q. Specifically, S equals to JQ dash and R equals to KQ, where Q dash is the complement of Q. D flip-flop to T flip-flop conversion. A D flip-flop can be easily converted into T flip-flop, allowing for simple toggling behavior, especially in counters. T flip-flop function. A T flip-flop's primary role is to toggle its output from 0 to 1 or 1 to 0 whenever its T input is high and a clock pulse arrives. D flip-flop abilities. Since D flip-flop next state is simply its D input, we need to make D equal to the derived next state for the T flip-flop. The T flip-flop is to toggle its next state. Q of T plus 1 must be Q dash of T. If it's not to toggle, Q of T plus 1 must be Q of T. This behavior can be achieved by spelling the D input of the D flip-flop to D equals to T XNOR Q of T. When T is equals to 0, D equals to Q of T. So Q of T plus 1 equals to Q of T. No change. When T equals to 1, D equals to Q dash of T. So Q of T plus 1 equals to Q dash of T. Toggles. This conversion demonstrates how an XNOR gate and can enable a D flip-flop to exhibit toggle functionally circuit for application will be like binary counters. Virtual summary. Flip-flops conversion circuits. These diagrams illustrate the minimal logical addition requires to convert one flip-flop type into another flip-flop. SR to D conversion. An inverse connected between the D input and the R input of an SR flip-flop efficiently transforms into a D flip-flop. SR to JK conversion, combinational logical involution, AND gate and invert is used to generate the S and R inputs from the J and JK and current Q output. D to T conversion, and XNOR gate is placed between the T input and the current Q output, with its results feeding to the D input of the D flip-flop. These transformations highlights the power of combinational logic in customizing the sequential circuit behavior. Conclusion: Mastering the flip-flop conversion. Flip-flop conversion is an indispensable skill for an digital designer, offering visuality and efficiency in complex circuit creation. Flexible design. It provides a powerful tool for designing digital circuits that can adapt a specific requirement without effect, efficient hardware changes. Memory, logical memory, a deep understanding of excitation table and Boolean algebra is critical for successful and optimized conversions. Optimized systems empowers designers to create more efficient and robust sequential logic systems with confidence, leading to better performance. Efficiency resume converge conversation enables to efficient use and adoption of exciting flip-flop circuits, saving time and resources in the development. Thank you.